Good morning, everyone, and to the brave souls who, after last night, actually managed to get up in the morning and come here. Good. So, because of the business meeting, I guess that's why they scheduled the talk, because the motivation is actually the conference location problem. This is the problem that we've just discussed right now. And where should one have a conference? In a place where there are 5 thermal baths and it's very hard to get to and students aren't going to come and we're going to have 30 people? Or in a place where there are many students and is maybe less interesting, but a lot of students can come and enjoy? So it's always a question. But in our particular case, so we have the world, and we map on the world all the people who are interested in CPM. And then we ask ourselves, all right, so here are the people who are interested in CPM. Where are we going to do the conference? So we say, where is it logical? Well, we can do it in Antarctica, for example. Or we can do it in Siberia. Or we can do it in Greenland, or somewhere in the Marshall Islands, or someplace like that, or in Ischia, or in an interesting place where we can all enjoy. So that is one option. However, another option of doing it is to say, why don't we look at all the people that are interested as points in space, for example, and look at a center location at one point, this one, that is actually whose maximum distance from all the other points is the smallest. So at least we make it easy for people to get to the conference. So that is one option of actually locating a conference. Now I know that our community doesn't like that, and that's why we someone was saying yesterday, let's do it in Iraq, next year let's do it in Kashmir. So we are more adventurous people. But sedate communities would say, all right, let's find a point whose maximum distance from all the points is smallest, and this is actually called the consensus or center string problem, and it's been very, very well researched. Because we are strings and not people, so our distance is actually the Hamming distance, stringologists. So what we're going to actually do when we say that we want the maximum distance from all the points to be minimal, smallest, so what we're going to say is that these points are strings and the distance is the Hamming distance, and we want the Hamming distance to be the smallest. Now, so formally, the consensus problem is defined as a set of k-strings of equal length and a given radius, and we basically say, is there a string S such that the maximum distance between S and all the other input strings Si is not bigger than the given radius? So if our strings were like here, CCCTGT, CAATGC, and ACAAGC, the string CCATGC actually has distance 2 from each one of these input strings. So this is the center string problem, and as I said, it has a very varied history. Francis and Littman proved that the problem is NP-complete even for binary strings, and once a problem is NP-complete, then what can you do? There are 3 directions that one can follow, and all 3 were religiously followed by the community. The first one is to say, okay, we have a number of parameters here. So the number of strings, the length of the strings, and D. So let's look at K, which is the number of strings, and say, what can we say about a small number of K? Maybe we can do that fast. Another direction is look at the fixed parameter tractability. What happens if we fix any of the parameters? And the third is, it's an NP problem. It's an important NP problem. NP-hard problem, because obviously we need to schedule conferences. So let's look at approximation algorithms.
Is one a special case of 2?
One is a special case of 2, but when people say about fixed parameter tractability, they say, okay, fix K, And do you have a polynomial time solution? And so yes. But one says, look at some small k and get it linear. How fast can you get it? So it's not exactly a special case. So, and whereas you answer number 2 in a general answer, number 1 is a cottage industry, because you say, all right, I know how to do it for 3. Who gives me 4? All right, we know how to do it for 4. 5. Does anyone give me 5? So that's the difference between 1 and 2. So as I said, so for small k, how small can it be? Well, 2 is easy, but 3 was done by Graham, Niedermeyer, and Rosmanith in 2001. That's a linear time solution. Boucher, Brown, and Durachet gave a linear time solution for 4 binary strings. With our friends, with our Korean friends who, alas, did not come here to CPM, we optimized both radius and distance sum for 3. We've done some work for 5 binary strings and showed that although in general one can solve the problem in O of L to the K, where L is the length of a string, so one would expect that if you're talking about 5 strings, the time is going to be L to the 5. You realize that instead of L to the 3 or L to the 4, all these were done in linear time. And we showed that for 5 binary strings, we can do it in L squared time. Obviously, at some point, it couldn't stay linear, since the problem is NP-hard. So the question is where, of course. As far as the fixed parameter tractability, you can see that a number of people did work starting in '97 and show that for fixed L, K, and D, there was a lot of work that was done. And as far as approximation are concerned, a p-test was given by Lima and Wang in 2002. It's a p-test, but it's not practical. Something that is amazingly good in real life is rounded LP, because you can actually write a linear program for the center string problem, and these things run amazingly fast and give very, very good approximations. So there was a history of that also. Of course, how fast they run depends on how many variables you're going to have in your LP, and the smallest number of variables that one can have is the set of column types times the alphabet. But today, actually, I want to talk about another motivation. I mean, I spoke about that because it introduces the problem and because it followed exactly from the discussion before. But what we're interested, actually, is in clustering. And clustering is, well, obviously, we all know it's important, but it's one of the solutions also for indexing, because in some sense, you want to index a lot of stuff, and people spoke about that. Gene spoke about that in his talk. You have huge data. You want to index it in some way. And so how about if you take all these points and say, maybe we can cluster them into some centers. And at that point, when I want to find who is closest to me, let me find the center closest to me, and then I'm already in the neighborhood of the strings that are closer to me than others. Clustering, of course, has a lot of motivations. One need not talk about it. But you can see that the problem, in some sense, is a generalization of the center string problem, because you're not talking about one center, but you have a bunch of centers, and they are the centers of the clusters. So what you really have at this point is some number, in addition to the points in space that give us the same parameters we had before, i.e. k points, L, the length of the points. We also have C, which is a number of clusters, a number of centers that we want to have. So you can give that as a parameter. Obviously, you can always do, if you know how to do these things fast, you can always do some sort of a binary search to find what's your best. And you're going to need to have some objective function that you need to either maximize or minimize on how you divide the points into the sets. So this is the problem that we're interested in this talk. And we're going to discuss 3 types of objective functions. The basic thing we start with is the Hamming radius clustering, which is basically the consensus string problem, the center string problem, the one that we spoke about until now. But having said that, that is one center, we now can have three types of measures or functions that we can look at and that we do look at it in this talk. The first one is the HRC problem, which the CHRC, which basically means we want to partition it into C sets, and each one of them has to have a center, and all the points are going to be within radius d of one of the centers. So that's number one. Number two is seemingly an easier problem. It basically says we want to partition them into, again, into C sets. Each one has a center and the radius is d. But this is, it's called HRLC. The L is local. The center has to be part of the input set. Now, in some sense, it makes it easy. In the C center, in the one center string problem, the one that was discussed until now, if you're going to look at the local version, then it's easily polynomial. Just try each one of the points that you have, see who has the smallest distance, the smallest maximum distance, and choose that. You can't get any more polynomial than that, so it's very easy. But here we're going to see that the problem is not easy at all, even if you allow the centers to be part of your input set. And finally, we look at another version where you have C sets, again, each one has a center, but we want the sum of the radii not to exceed d. Rather than each one d, but we want the sum, which means that you're allowed to have some centers that have larger radii, a larger radius in some centers, whereas in other clusters you have very small radii, so that would be okay also. So these are the three versions that we considered here. And so an example of the differences between them. This is the obvious, easy HRC problem. So 2 HRC would mean if this is your input and you say let's cluster it into 2, we actually can have one center which is just AAAAA, and then S1 and S2. Each one is a distance 1, Hamming distance 1 from this center. And we can have another center, BBBBB, and each one of S3 and S4 is just within distance 1. So that's easy. However, if what we want is to have the local, then our centers have to actually be parts of the set. Then in this example, we can't already have d equals to 1. D is already bigger, is equal to 2, because we have to choose one of them to be the center. So in this case, talking about the goats of yesterday, we have ba as one of the centers, and it's actually distance 2 from S1 and S2, whereas BBBBA is distance 1 from this set. Now, it's easy to see that it's in 2H RLC we just showed for d equals 2, and it's also easy to see that for d equals 1 it's not. Whereas in the 2 HRC, we actually had d is equal to 1. And finally, as far as if we're looking at the sums, then what we do is we actually add up the distances. All right. So what did we do in this paper? We considered two things: parameterized complexity and approximations. As far as the small k, we did not, it's not too meaningful because one center we know how to do. And we'll see that when you're talking about clustering, to say, all right, let's cluster it always into 1 or into 2, it doesn't mean as much, and therefore, sorry, not that you cluster it into 1. If you have only 3, if k is equal to 3, which means you only have 3 points, then what does it mean to have 3 centers? Take each one of the points to have its own center. So it doesn't make much sense to talk about small k, small number of points, if you're talking about clustering it into many centers. Now, so what you have here is a table of the results that one can think of, and that anything that one can think of, we tried to do. So if you fix C, you can either fix C, the number of centers, or K, the number of strings, or D, the distance. Or you can even fix D and C, or L and C. Or you can fix just L, the length. So if you fix each one of these parameters, what happens? So for each one of these problems, we wrote the what we could prove. And whereas as I told you, it's fixed parameter tractable for every parameter if you're talking about one center. Here we have a number of NPC results, and there are also some question marks, things that we haven't proved, and we don't know whether they're polynomial or not. So I'm not going to prove each one of these, even though... Jessica, who finished her master's, and this was part of her master's thesis, sent me 500 slides of the talk proving each one of these things. Now, she didn't come because happily she gave birth about 2 weeks ago. Our community is a blessed one. So all my students, I'm presenting all the talks here because all the students in all these papers either gave birth or are going to have a child born within the next month or something like that. So none of them could come, and that's why I was stuck with it. So I told them, the very least you can do is send me slides. So she sent me 500 slides that prove all of them. So I decided I'm not going to prove all of them for you. And what I'm going to do is just prove this column, which can be done in one proof, and show you that polynomial time, when it exists, is actually easy and not very illuminating. The big surprise here was that you fix some things and you already get NP-complete. I mean, you fix the length. Length equals 2. Fixing the length in the one center string problem makes it very easy. But here you fix the length and you get an NP-hard problem. So that was the surprise. So what I'll try to show you is the polynomial time and one of the NP-completeness. And maybe approximations, but I didn't see when I started, so I don't know when I'm supposed to finish. All right. So the first thing we're going to show is how HRC, HRLC, and HRSC, so forget about all the R's and S. Just think about the center string problem with radius D, which is HRC, the vanilla version. And we're going to be, for a fixed K, we're going to be solving it in polynomial time. How do we do that? Well, okay, K is fixed. That's the number of strings we have. C is given as an input. If K is less than or equal to C, then obviously it's polynomial time. Take each one of them as a center and you're done. Because again, like I said, if K is small, we don't care. So if K is smaller than the number of centers, then each one of your inputs is its own cluster, and that's happy. Do it in constant time. All right, otherwise, C is less than K. But K is still fixed. So your input is less than K, the number of centers. K is still fixed, so K to the K is also fixed. But all the options for partitioning all the strings is C to the K, which is less than K to the K, which is a constant. So you have a constant number of partitions to look at. So for goodness sake, take the constant number of partitions, and for each one, find the consensus center. And you can do it in polynomial time for each partition, because that's already one center. So partition. Look at each group. It's one center where K is fixed for one center. We know that it's fixed parameter tractable. So, so once you are looking for one center, you can do it in polynomial time and then choose the partition that's best. So whenever, and indeed in the one center case, the fixed parameter tractability was easy because of this, because it's really very easy. But so all of these, whenever you fix something, you expect it to be polynomial. But alas, it turns out not to be polynomial in every case. So let's show how if we fix D, and we even fix D to 1. So we're looking for D is equal to 1. That's our diameter. That's our radius. We do not allow any clusters to have more than one error. And still, we're going to have an NP-hard problem. Okay, so in fact, we're even going to take a binary alphabet. So we'll make it even easier. And the reduction is going to be from vertex cover for triangle-free graphs. Now, what are triangle-free graphs? This is not a triangle-free graph because you see a triangle. This is a triangle-free graph because there is no triangle. So triangle-free graphs are graphs where there are no three nodes that are connected to form a triangle. And the vertex cover is NP-complete even for that kind of graph. So that's our input, a triangle-free graph. T is the size of the vertex cover that we are allowing, and we want to reduce that to the HRC problem where the radius is 1. So here is what we're going to do. The construction is easy enough. You take your graph. Every edge write it as a bit string where the length of the bit string is going to be the number of vertices that you have. And so you light up just the two vertices that are connected by this edge. So this purple edge here is connecting 1 and 4, so these are the bits that are on. The blue edge is connecting 2 and 3, so 2 and 3 are going to be on, etc. So you end up constructing this kind of binary matrix. And the parameter that you're going to choose is going to be, the C. The number of clusters that you want to use is going to be T, is going to be the vertex cover. As we said, the distance parameter is 1. Now you can see quite easily why this thing is going to be NP-hard, because, so we need to show the two sides. So let's start with assuming that this thing has a vertex cover of size 3. So what we need to show is that we can actually cluster it into three clusters, where the distance between the center string and each one of the strings in the cluster is equal to 1. Now this is obviously going to be true, because what does a vertex cover mean? That all of these edges are going to have one of their sides being equal to 4, which means that if we look at, where is that? Actually, it's this one. So if we look at the 3 covers the green edge, the blue edge, and the red edge. These are the vectors of these edges. And because 3 covers all of them, they have to have a 1 in number 3, in vertex number 3. So 0, 0, 1, 0, 0, 0, 0 is within distance 1 of all the other strings, because one of them is the 3 and the others are whatever it is, but they're covered by this. So you're not going to need more than the vertex cover in order to have these strings. And the other side needs a bit more work to show, but basically, actually, let's see if I want to do this. Alex, what time did I start? When am I supposed to finish?
I think you have another
5 minutes. So let's skip the NP-hardness, and let's do a little bit of approximations. See, I told you, this is after I cut down the 500 transparencies. Well, move on. Okay, approximations. So I'm going to, again, give a taste of some of the approximations. In fact, no, what I want to say is the following. As I told you, the LP for the center string problem is amazing. It's unbelievable. You run the LP, you really don't need anything else. So what I thought, and that's what I told Jessica when she started her master's, I said, listen, figure out some sort of an LP for the C center string problem, and that is going to be a great solution. Now, it wasn't exactly fair what I told her, because Chaim Pariente, who had done his PhD on the one center string, tried to do an LP for C, for the C center string problem, and it didn't succeed. But I told her, look, you want to start doing a master's, so think of something easy. He was doing a PhD, didn't manage, so you can do it for your master's. So she did. She came back with an IP, but she couldn't prove how good the IP is. So I told her, well, if you can't prove it, run it and see how good it is. She ran it, and it was awful. So then she figured out why the IP doesn't relax well, why the relaxation doesn't work well. So I told her, all right, so let's look at the problem now. Let's do the dirty work. And that's why we started looking at the NP-hardness and the approximations. So let's show a few approximations. And I don't know if I'll manage to do all of these, but let's start with this lemma. Suppose that SD is your input for CRC, and let's assume that that S1 to SC is a partition of S into C clusters. So we don't know what it is. The problem is NP-hard. We don't know what it is. But we do know that there is some partition into C clusters with a radius not exceeding D. But let's also assume something else that's nice and easy. and that is that these clusters are not too close to each other. So there is a distance of at least 2D between each cluster. So at this point, the optimal solution can be easily approximated in polynomial time. And the main idea here is the fact that the Hamming distance does follow the triangle inequality. And therefore, any 2 points in a cluster, because their distance from the center is less than or equal to d, their distance from each other is less than or equal to 2d. And if the distance between all the clusters is more than 2d, then these clusters don't actually go into each other. And so therefore, you now have an easy way of partitioning. Because if we had a representative for each cluster, then we associate all the strings to this representative. And then we use a known approximation for the one HRC, and there are a lot of them, even p-tas, as we said. So that's what one would like to do. And so all you need to do really is try them out. Take a bunch of take C elements and check. Construct the clusters around them of all those that are less than or equal to 2D from these C elements. And you're going to have your approximation. So this other lemma says that if you have, again, an input for the CSRC, and now something else happens. We don't know that all the clusters are separated from each other, but we do know that the centers of the clusters, at least, which we don't know what the centers are, but the centers are at least distance 4D from each other. Then again, we can approximate the optimal solution in polynomial time. And the way that we do it is basically by showing that if the centers are within distance of 4D from each other, then all the elements of all the clusters are within distance of 2D from each other, and therefore that problem we already solved. So that's what basically gets done in this proof. And I'm not going to go into the details, even though they're nice and colorful. And finally, we can actually provide a polynomial time approximation for the 2HRSC problem, where the ratio is 3 times the ratio of the 1 HRC problem. So within a factor 3, you can approximate anything, even in a general case, by assuming, it's enough to assume that the distance in one cluster is less than or equal to R1. The distance in the other cluster is less than or equal to R2. Here we're talking about the sum problem. Well, if that's the case, again, the approximation algorithm is going to say, well, choose 2 points, SA and SB, and look at, and every point that comes in, ask yourself, or check, if it's closer to SA or closer to SB, and put it in the one that's closer. At that point, we can prove that what happens is that if we chose SA and SB in 2 different clusters to begin with, then the approximation ratio is going to be no less than 3, because either the closer one was in his own cluster or he wasn't in his own cluster. But if he wasn't in his own cluster, it means it was closer to SB than to SA. If that's the case, because of triangle inequality considerations, it cannot be that far away from SA either, and therefore the approximation is still going to be bounded by 3. So more or less with hand waving, that would prove the general case. In the paper, there is also a nice heuristic that worked out very well, and which we haven't been able to prove why it's nice at all. So, so let me skip to the open problems. Forget the analyses here. All of these analyses, believe me, are in the proceedings in painful detail, so you can look at it there. So obviously the first question is, if the heuristic algorithm does well, what is its approximation ratio? That we haven't been able to prove yet. There are gaps in the parameterized complexity table. You saw all those question marks. Every question mark is something that can be filled in. Is there a p-tas for CHRC? No idea. And the big question, the one that started this whole thing rolling, is can we approximate it using LP or SDP or one of these fast approximation algorithms? Because that would be very nice. That's the kind of thing that you can actually run in reality and get a nice approximation. So if that can be done as it's done for the center string, that would be beautiful. Okay, thank you very much.
Quick questions?
Yeah.
Okay, you go for the question there about a p-task, maybe a simpler question. So you showed a 3 approximation, right?
Mm-hmm.
Is there any reason to believe that there's something better than 3? Or, you know, is it 2?
No,
or?
yes, obviously, yes. Forget about p-task. One can always also squeeze constants. Yeah. We have 2 approximations for some cases, but in general, the best we could do was a 3 approximation. So I don't know. I mean, forget about p-task. I don't know if it's not approximable.
Vertex cover is doesn't have a p-task. We know that.
Yes.
As there any reason? Do you see any relationships like the reduction itself is linear between the two?
Is the reduction linear?
Because in that case, it wouldn't be.
Yes.
There wouldn't be a p-task. The reduction is linear in V plus C, yes. But it's only in one of the cases. So what was, I mean, So,
I have to go back at the table and
okay.
look. It didn't
But
work
if
for
it-
all the functions. So some of them we don't even know what's happening. But
Okay.
in that particular case, you're right. So we know that for that case, we're not going to have a p-task, and you can work on the, and one can work on the constant. In
Yep.
the others, we don't even know if it's NP-hard or not. And so there's a lot of stuff still to be done here, 500 slides notwithstanding.
Any more questions?
So when you say problems are NP-complete for a fixed parameter, that formally that means something like W1 complete?
Yeah.
Something like that. Right. Okay. Any more questions? Okay, so let's thank Amir once again.